Hi everyone, my name is Puyan and I'm presenting a new partial p-Wasserstein-Based metric for comparing distributions. In this work, I collaborated with Dr. Sharat Raghvendra and Kai Zhang. For two probability distributions mu and nu, let gamma be a minimum cost transport plan that transports all the mass from mu to nu. Here, the cost of transporting a mass of delta from point x to point y is defined as delta times the Euclidean distance of x and y to power p. And the p-Wasserstein distance between mu and nu is defined as the total cost of all mass transportation according to gamma whole to power 1 over p. For a parameter alpha between 0 and 1, the alpha partial p-Wasserstein distance between mu and nu is the cost of the minimum cost transport plan that transports alpha mass from mu to nu. For high values of p, the p-Wasserstein distance is sensitive to small geometric differences, which makes it a powerful metric for comparing distributions. However, adding a noise of delta to the distributions can cause the p-Wasserstein distance to be distorted by a value as high as delta to power 1 over p, which makes it sensitive to outliers. Furthermore, for the empirical distributions, the rate of convergence of the empirical p-Wasserstein distance to the true one is n to the power 1 minus 1 over 2p. And therefore, as p grows, the rate of convergence of the p-Wasserstein distance slows down, and for p equals to infinity, the empirical infinite Wasserstein distance does not converge to the true one. In this work, we designed a new metric called the robust partial p-Wasserstein distance, or in short, PRPW, where given two distributions mu and nu defined over a support x with a unit diameter, the PRPW distance between them is the smallest epsilon for which the cost of the 1 minus epsilon partial p-Wasserstein distance between mu and nu is most epsilon. So here you can see that our distance tries to transport mass of mu to nu, which are shown by the black arrows, until the cost of the transported mass becomes equal to the amount of mass that is not being transported, which are shown by green. We show four important properties for the PRPW distance. The first one is that it is a metric and satisfies identity, positivity, symmetry, and the triangle inequality. The second one is that it is robust to outliers, and the delta outlier mass can only distort our distance by at most delta. The third one is that it has a faster convergence rate compared to the p-Wasserstein distance, as the rate of convergence of the empirical PRPW to the true one is n to the power minus p over 4p minus 2. Note that for p equals to infinity, our distance converges at a rate of n to the power minus 1 over 4. The fourth one is that our distance retains the sensitivity of the p-Wasserstein distance. So for two distributions mu and nu that differ in delta mass, assuming that the 1 minus delta over 10 partial p-Wasserstein distance between mu and nu is at least their Wasserstein distance divided by 2, then our distance will be a small constant times the minimum of delta and the p-Wasserstein distance of mu and nu. We extend the definition of our distance to a family of distances, where for a parameter k greater than or equal to 0, we define the p and k RPW to be the smallest epsilon for which the cost of the 1 minus epsilon partial p-Wasserstein distance between mu and nu is at most k epsilon. We interpret our distance using the OT profile. OT profile is a function that maps any alpha between 0 and 1 to the alpha partial p-Wasserstein distance between mu and nu. Consider the intersection point of this OT profile with the line k y equals to k times 1 minus x. And suppose this intersection point is x star and y star. Then our distance will be simply 1 minus x star. Using this interpretation, we can see that when we set k equals to 0 and for any p greater than or equal to 1, our distance will be simply the TV distance between mu and nu. Furthermore, as k goes to infinity and this line becomes a vertical line, our distance also goes to be 1 over k times the p-Wasserstein distance between mu and nu. Finally, we show that for p equals to infinity and k equals to 1, our distance is simply the Levi-Prokhorov distance between mu and nu. We finish this presentation by showing some experimental results on the image retrieval task. So consider a labeled dataset consisting of 2,000 images from the MNIST dataset and a query dataset of 50 images. Here we compare the performance of the RPW distance with one-Wasserstein, two-Wasserstein, and TV distances for the image retrieval tasks in the presence of noise and shifts in datasets. In the first scenario, we add a random amount of noise between 0% and 10% to a random pixel of each of the labeled dataset and perform the image retrieval task. And as we can see, our distance and TV distance performs much better than the Wasserstein distances. Second, we shift each of the labeled images in the labeled dataset by 2 pixels and see that our distance performs much better than the other distances, and also 2 Wasserstein is better than 1 Wasserstein and TV. In the third scenario, we add both noise and shift to the datasets, and we can see that the gap increases and our distance performs significantly better than all three distances. Thanks for your attention.